All right, so the title of this module is Solving Linear Ordinary Differential Equations via Laplace Transforms and via State Space Representation. Solving linear ODE via Laplace transform and via state space representation. So let me give you some brief background before we jump into the MATLAB part 2 of it. So let me show you how to solve, let me remind you how we solve scalar differential equations. Okay, so let's just consider an example. So 2y double dot minus y dot plus 5y is equal to cosine of 3t. You certainly know how to solve this manually. So you take the Laplace transform of the entire equation. So you will end up with, keeping in mind all the initial conditions, okay, you will end up with this. Then you solve this algebraic equation with respect to y of s. You obtain y of s. And once you get y of s, you need to take the inverse of y of s, inverse Laplace transform of y of s, to obtain y of t. Okay, that's your usual procedure. And let me stop at this point and then let the MATLAB handle the rest of it so that you take advantage of MATLAB rather than doing this manually. So then the solution is basically taking the inverse Laplace transform of it. So let me show you how you do this with MATLAB. So, so here it is. You define your symbolic variables. My symbolic variables are going to be time, t, Laplace variable s, and Laplace transform y of s, which I call y at this point. Then I define my ODE. So if you go back to the PDF file, you will see that this is exactly the equation that I have, with the cosine being transported to the left-hand side, so the entire thing has to be equal to 0. This is my ODE, and this is how you define the derivatives and double derivatives as functions of time. You take Laplace transform via the command called Laplace. You have to be a little bit specific about this. Again, if you, as always, if you see a new command and you want to know more about it, you just type up help Laplace in the command window, and MATLAB will give you everything you need to know about it. So you take the Laplace transform. By default, MATLAB understands what is the time variable t and what is the Laplace variable s. You might want to double specify it in here as well. So MATLAB is going to take Laplace transform of this entire equation, and time t is a time variable, and it will end up being a function of s, which is Laplace variable. Then, if you remember, if you go back to my write-up, you need to solve the algebraic equation with respect to y, to obtain y of s. In order to do that with MATLAB, not manually, but with the help of MATLAB, it's very easy and quickly, you can do this trick. You're going to do the substitution. So remember, the command subs substitutes certain symbolic variables with perhaps other symbolic variables or the values for those symbolic variables. So we're going to do the substitution in the Laplace transform of the original differential equation. So I have obtained the Laplace transform of my ODE, which I call LODE. So, and in this equation, I'm going to replace this Laplace transform of y of t with y, initial condition for y of 0 with 3, because this is my initial condition, and y dot at 0 with -1. Okay, so you list, first of all, in the figure brackets, you list things that you are going to replace, the old values, and then in another figure brackets, you list the things, the new values for the corresponding things that you're going to replace. So it's pretty self-explanatory. It doesn't take too much. And then what? So once you've done that, you are going to look for y. So essentially, you're solving this equation with respect to y. For this, you talk about solve command. We've talked about solve command that allows you to solve both linear and nonlinear equations and systems of equations. So this is another use of the solve command. So it's going to solve this equation. In that equation, LODE, so LODE will be equal to 0, and in that LODE we replaced Laplace transform of y of t with simply a variable y. Okay? And I'm specifying this here so that we're solving this with respect to y. That's going to be my solution. That's going to be y of s. And then, so you just want MATLAB to show what that is, and then you take the inverse Laplace transform of this. So it's done by I Laplace of y. Okay? So this is going to be your solution. Sometimes it's that MATLAB will give you the solution in a convoluted way. So you can apply commands such as simplify or pretty. So MATLAB will make it look like something that you would write manually. So let me run this for you and explain what MATLAB eventually yields. Okay. So here it is. So first of all, y of s is given here, and I point out that this is Laplace transform of the given second order so this is y of s. So whatever that is, I should probably replace this. So Laplace transform of, how about I say y of t. Okay, so let me rerun this just so that you have everything clean and nice. Okay, so Laplace transform of y of t is given as such, and then you take the inverse Laplace transform, which is going to give you the solution of that equation. That's going to look something like this. So MATLAB will give it to you in this fashion. So it's e to the power of t over 4 multiplied by cosine of, sometimes you have to help MATLAB a little bit. So for some reason it doesn't give you the actual value of the square root of 39, so you would have to figure this out on your own. So square root of 39 times t over 4 minus, and so on. So this is going to be the solution in the time domain of this differential equation. So this is how you do this. You can also plot the solution. So once you obtain the solution, you can use the command called easyplot. So easyplot is really an easy plot. You just type up the name of the function that you want to be plotted, and that is called solution Laplace in my case. You specify the limits between which you want this to be plotted. If you want to apply a grid, you apply the grid, but that's what the graph looks like. So this is my solution. This is the plot of the solution of the differential equation. Okay, so y of t versus t. Okay, this is how you do. This is how you solve scalar differential equations using Laplace transform. And my next example would be to show you how to solve systems of differential equations using state space representation, but that would have to be done numerically. So let me give you a little bit of a background on this. So next topic is numerical solution using state space representation. So let me give you a typical problem, but that problem doesn't have to be limited by this equation. But in some vibration problems, if you're a mechanical engineer, you will deal with this Euler-Lagrange equations. But again, any differential equation can be solved using state space representation, and I will show you how to do that. Let's say you have this system of n degree of freedom system, which is described by this differential equation. This is the initial condition for the position and for the velocity. Again, the similar kind of problems could be found in electrical engineering setup or chemical engineering setup. So it's not just limited by the mechanical engineering setup. So M is an n by n matrix, B is an n by n matrix, and K is an n by n matrix. F is a n-dimensional vector. How do I bring this second order differential equation into the system of the first order differential equations? For that, I introduce the so-called state variables. X1 is going to be equal to the vector x. Remember, x is an n-dimensional vector. So if you're talking about the mechanical engineering problems, then x would be a vector x1 that has components x1, x2, x3, and so on, xn, which typically represent the positions of the parts of the system. So I'm going to introduce my state vector x1, which is equal to x, and my other state vector x2, which is equal to x dot. Okay, velocity, vector of velocities. And I'm going to start taking derivatives of x1 and x2. x1 dot in terms of state variables x1 and x2 will be equal to x2 dot, x2. And x2 dot is x double dot, and x double dot I can rewrite in terms of my state variables in following form. Times x, but x is x1, minus m inverse times b times x dot, but x dot is x2, minus m inverse times f of t. Okay? This is the so-called state space representation of my system. Equivalently, I can rewrite, why don't we introduce the matrix A tilde, which is going to be a matrix of zeros, n by n zero matrix, identity matrix of dimension n, and two other blocks. So this is a block matrix, 2n by 2n, each block of which is represented as follows. My B tilde matrix is matrix of zeros, n by n, and m inverse. Okay, and I'm going to introduce my generalized state, x tilde, which is x1, x2. In that case, I can rewrite this system of equations, this one, as follows. X tilde dot is equal to A tilde X tilde A tilde X tilde plus B tilde times f of t. Okay, with the initial condition x0 and x0 dot, which is given a priori. Okay? How do I translate this into the MATLAB? Because MATLAB understands this. MATLAB doesn't know how to solve second or third order differential equations numerically. Those equations have to be converted into the state space form or state space representation. And this is what we just did. So let's see how we can handle this in terms of MATLAB. All right. So let's go back to my original equation, which is mx double dot plus bx dot plus kx is equal to f of t. And let me introduce the matrices here. So my matrix M, let's say I am dealing with the, if it's a mechanical system, 2 degree of freedom system. So my matrix A, my matrix K, my matrix B, I'm introducing my initial conditions. And as if we go back to this, so I need to make up this matrix A tilde and B tilde. So this is how I do that. So call them A1 and B1 instead of A tilde and B tilde. So it's going to be the matrix of zeros, identity, then M inverse K minus M inverse K minus M inverse B. And then for B tilde, again, according to what we have just obtained. And then I'm going to implement the command ODE 45. So MATLAB knows how to solve the first order systems of first order differential equations via the command ODE 45. And what we did by doing the state space representation is we converted the second order differential equation into the system of the first order differential equations. So in this case, MATLAB can handle this. I'm defining my initial conditions, x0, implementing ODE 45 command with the right-hand side defined in the subroutine RHS. RHS stands for the right-hand side. So RHS, MATLAB is going to look for that subroutine, which is right here. And at every step of integration of that differential equation, it's going to communicate with this subroutine RHS. So basically, it's that simple. You call ODE 45 command, you specify the subroutine where the right-hand side is hidden, the right-hand side of the differential equation, which in our case is A tilde x tilde plus B tilde times F. You define the interval of integration, so you're going to integrate from time 0 to time 10 seconds with the initial condition given, which is what I defined earlier. So MATLAB communicates with the right-hand side, with the subroutine RHS, where you define your right-hand side. In order for you not to redefine matrices A1 and B1, since you already defined them here, you must declare them as global variables so that MATLAB knows what they are. That subroutine RHS is going to have two variables, t and x. T stands for time, and your right-hand side f of t is defined precisely as this. So I made it up. I said, the first component of the time will be, of the f function will be 2t. The other one is 5 times sine of 10t. Depends on the problem, obviously. And my right-hand side is A tilde times x, or A1 times x, plus B1 times f. Okay, so that's consistent with what we had before. So MATLAB is going to solve this differential equation. X dot is equal to ax plus A tilde times x plus B tilde times f, numerically. Okay, once it's done, it's going to catalog all its findings into this arrays of data. So t is going to represent the time, because time was defined t here, and x, capital, is going to be a matrix. The number of rows of this matrix is going to be large because so matrix x, capital, is going to have two columns. One column is going to stand for the value of x1, and second column is going to stand for the values of x2. And in order to plot them, you plot t versus the values in the first column of x. And then in order to plot x2, you plot t versus the values in the second column of x matrix. Okay? So if you run this, So this is going to be my x2 versus time, and this is going to be my x1 versus time. Okay? The first component of the vector x and the second component of the vector x. Remember in the beginning when we started conversation, so that vector x probably stands for the position, if it's a mechanical system, stands for the positions of the components of the system. So this is the first position versus time, this is the second position versus time. Okay? So this is how you integrate the differential equation, so systems of differential equations via state space representation. And I complete this module.